My student friends, I am Shivraman sir, and I welcome you today to this live lecture on a revision lecture on coordination compounds. Okay. I thank you for your enthusiastic participation. I hope what I teach today, I have purposely put lecture one because coordination compound is a very vast topic. It has a total weightage of something like 4 to 6 questions in any of the entrance exams, JEE mains or NEET. So we basically divide to three parts. The first part will be today we talk about Werner theory. Then we will talk about the types of ligands. Go over to quickly taking an example of compounds, coordination compounds, so that what we can do is we can understand practically while writing the name what are the rules for nomenclature. So this is what we try to achieve in 1 hour. Next Saturday, again at the same time, we will then go over to geometrical isomerism and structural isomerism, one part, and then we will go over to valence bond theory and crystal field splitting. So these are the three sections of coordination chemistry in which maximum importance is to Werner theory. What is Werner theory? Nomenclature, and of course isomerism. And we go to this. I'm trying to compact the whole thing. Is it clear? So we start off with what you call first point. What is a coordination complex? See, basically, coordination complex is a salt. So when you talk of a salt, what happens is we have two types of salt. One is called as double salt, and the other is called as um, coordinated salt, or a coordination complex. That we'll put it at the moment as coordinated salt or a coordinated complex salt. That would be more appropriate. A complex salt. Okay. Now this is where we have the first question which is generally asked in any entrance exam. It's clear. So you have double salt. That is, example is Morse salt. Morse salt is ferrous ammonium sulfate. So you have ammonium sulfate, NH4 whole twice SO4, and aluminium sulfate, ferrous ammonium sulfate. So sorry, ferrous sulfate, FeSO4. Okay, and you have X amount of say H2O. Then you have carnallite. So carnallite will be KCl, AlCl3, and then you have I think 6H2. So more salt, and you have alum. Okay, alum will be aluminium sulfate, K2SO4. So you have K2SO4, Al2SO4 whole tribe, and H2, a certain amount of H2. It is clear. See, here you have to understand that. So this is one direct question which they can ask. That is, which is a double salt? So out of the four destructors, what is a double salt? If you put it in water, it's going to dissociate completely, and you're going to get test for each and every ion. So, for example, if I put more salt, okay, understand one more tricky question in this, that in more salt you have a non-metal sulfate with a metal sulfate in a ratio of 1:1. Here you have an alkali metal chloride with an aluminium chloride ratio of 1:1. You have an alkali sulfate with aluminium sulfate in a ratio of 1:1. So this is why it's called double salt. And the second reason is, of course, that when they dissociate, they give what do you call qualitative test, positive qualitative test for each and every ion. So you will get a test for ammonium ion, that is to put Nessler's reagent over here. You will get a brown precipitate, sulfate ion, OS plus barium chloride. If you put it, you put barium chloride, consider barium sulfate. Fe plus 2, that Prussian blue, you will get a. Similarly, over here you will get test for potassium chloride, silver nitrate will give precipitate. Aluminium chloride will give you aluminium ka test, OS plus NH4, OH plus NH4Cl will give gelatinous white precipitate. Again, potassium will get the test, sulfate, aluminium, so on. So it gives text. Whereas in complex salt, example we have is suppose if I have this K4FeCN6, okay, here when I put it in water, what happens is then it dissociates to form 4K plus FeCN6 minus 4. So you can see over here, this will only give test for potassium ion and it will not give a test for Fe ion because this is coordinately linked to the central metal atom or ion that is Fe. It's clear. So we are talking about, so I have this is a very small discussion I mean. So this is the kind of question I told you. Basically, you have more salt, shonite, and carbonite. So this one was alum can be called as shonite. So they are all in the ratio of 1:1. Non-metal sulfate with the ferrous sulfate. Then this is ratio of 1:1. Potassium chloride, alkali metal chloride with aluminum chloride 1:1, and alkali metal sulfate with aluminum sulfate 1:1. Is this point clear? Now, when we come to coordination compounds, let us discuss further. What we have is when we talk about so what we have over here is now when we talk of a complex salt, so we come to Werner's theory. Quick look at Werner's. So what did Werner's theory say? According to Werner's theory, he said, look, let us take this. If I take this coordinated salt, FeCN6, so what happens is this Fe has a charge, it was K4FeCN6. So this was minus 4. Okay. So what he said was that whatever is, there is a primary valence. The primary valency is nothing but the oxidation state. Then, how many ligands? So you have a metal ion or atom at the center, and you have a what I call. I'm taking something for granted because this is a revision lecture. I can't go to the very depth. This will be 6 lecture. Cyanide ions are called as ligands because they are electron donors to the electron deficient central metal atom, which has vacant p substitution or a ion. It's clear. The number of ligands is what we call as coordination number. Coordination number. Okay. So, and this whole thing is called as coordination sphere. The charge on coordination sphere. Charge on coordination sphere. Charge on coordination sphere is the sum total of what? Is the sum total of the oxidation state, that is the primary valence, plus total charge of the ligand. Total charge on ligand. So you have, so if your total charge is minus 4, let us say the charge of Fe is X, oxidation state, the primary valence. We don't know, let us say it's X. Okay. So coordination, number of cyanide ions, what do you call, attached to this by a coordinate bond is 6, and each has a charge of minus 1. So it will be minus 6. That becomes equal to minus 2. So X becomes equal to plus 4. So your primary valency or oxidation state of this is Fe plus 2. It's clear. Now what happens? This is called as residual valency. If this is residual valency, what happens? This has to be balanced. This is ion. To make it a salt, this anion has to be balanced by cations. So we have K4. That's how we got K4. In this case, you can have even a complex with this, that will be coordination complete. So K4 we use to balance this because each K plus is plus 1, so plus 4 to balance this to become a salt. It's clear. So in short, I told you what is, but what he said was that this secondary valence, okay, is attached to the central metal atom or ion. This is central metal atom or ion. The oxidation state is non-directional. It's just the valency, number of electrons lost or not lost. It could be a metal atom. But he said that the secondary valency, the coordination number, is what decides the structure of the bond. So we have a calcium structure. So if I have coordination number 4, he said that coordination number 4, he said that we have what we call the structure could be tetrahedral. If it is, or it could be square. If it is coordination number 6, he gave only one option. He said it is octahedral. It is octahedral. And here comes a very interesting. If you look at all the textbooks, you will find that the oxidation state, the maximum oxidation state, they have said when the central metal atom or ion can have is plus. Okay, this is a molybdenum what we call complex. But remember one that cerium, that is hexa, that is you have something like cerium, hexanitrate. So what will happen is you have 6, so this will be cerium plus 2, or this most stable oxidation state is plus 3 for lanthanide. This is minus 6, so this is minus. So here nitrate is acting as a bidentate ligand. So it will have a coordination number of 2. Are you understand? So whenever you are attending the question, the highest oxidation state of a central metal atom or ion, if highest is 8, then they are going as per text. Clear that highest is 8. Okay. But if there is 12, that means they are using reference to derive this question. And what happens is that then it will be 12. So they are using a reference. So in that case, 12 will be a more appropriate answer. Here. So this was one JEE question which I discussed. So further clearly said is primary valency, which is oxidation state. Okay, it is non-directional. Secondary valency, which is coordination number. So sum total gives a residual valency. This residual valency, if it is a neutral complex, not satisfied by anything. If it is negative, it is satisfied by positive ions. If this is positive, it will be satisfied by negative ions. As simple as that. So this was about Werner's theory. Okay, after Werner's theory, what happens is we will try to talk about ligands. We focus first on picking the ligands. So what are ligands? What are ligands? So ligands are species which act as electron pairs. They are rich in electrons. So they are rich in electrons. They can give electron pair, a dative bond, coordinate bond is formed. And who does it give to? An atom, central metal. Can it give to any central metal atom? Here is the question. So one of the questions which we asked in NEET was they gave compounds, and one was lead nitrate. So here lead nitrate cannot act as a complex. Why? Because lead is not a transition. So you have to understand when I say central metal atom or ion, that central metal atom or ion is either or inner transition. Because these are the ones which have a vacant p subshell accept the lone pair. This is one thing which you normally take for granted. And then the question is framed where one of the distractors is a non-transition. That is oxygen sulfur selenate name. So if lead will come in the p block, carbon, silicon, germanium, tin, lead. So lead will come in the carbon series. So it's not a transition. So any compound of lead cannot act as a transition. So remember this one. So ligands. When you talk of ligands, basically there are 3 types of ligands. One is a negative. One is a negative ligand. So we have OH minus, popular, chloride, and halo. I can say halo. Halo is Cl minus, Br minus, I minus. Okay.
Then you can have a very important when you talk of negative, which people don't understand because they will make a mistake here when you're calculating the charge on the coordination sphere. Because what is charge on coordination sphere? Charge of the central metal atom or ion plus the charge on ligands. That is dimethyl glyoxide. See, we have CH3, CH3. Okay, double bond N, O minus, double bond N. So your dimethyl glyoxide is having one negative charge. So if I say nickel dimethyl Ni and then I put it in bracket D and G. Okay. See what happens is this will be a neutral compound. It will have no charge, no residual valency. Why? Because nickel was +2 and each dimethyl glyoxide was -1. So 2 with -2 becomes it becomes a neutral compound. Is this point clear? Okay. So this was about what dimethyl glyoxide. So this is a negative. Then you can have neutral ligand. I'm taking only few examples, which I feel, and example where I feel there is something to talk about which will enhance your whatever knowledge. So we have neutral ligand. Example of neutral ligand is ammonia, water. Okay, these are neutral ligands. The more important is see when we say ligand or electron donors, positive charge does not come in. But there are two positive molecules, compounds or molecules which can act as ligand. See, NH2, NH2 is hydrazine. It should be a neutral ligand. Hydrazine when you treat with H plus. Here the H plus gets attached and so hydrazinium ion will be an example of a positive ligand which can be. Then we have one NO plus. See, NO is called as nitric oxide. Nitric oxide and nitrogen dioxide, each of them has one odd electron molecule. So if that odd electron it goes away, it becomes NO plus. But remember one thing, it can still donate electron from nitrogen. It has a low pair of electron. So this is called as nitrosodium. So this is probably taught, but then we do not remember because we generally think that negative ions and neutral complexes with low pair are good. Especially this is not a very critical question which we discuss. It's ground ring test. This has no relevance. So this was about ligands. How are they classified based on charge? This is clear. We can also classify ligands on the basis of denticity. Denticity means ligands can be composed of denticity. So what is denticity? Denticity means how many lone pair can one molecule. So you have monodentate ligand. So monodentate ligand is an atom. It's a molecule where it can donate only one lone. Okay, so we have OH minus, Br minus, NH3. These are all monodentate. Then we have bidentate. So in the neutral molecule, bidentate ligand will be ethylene diamide. CH2, CH2, NH2. So here this nitrogen and this nitrogen to be available for donation. This is how they donate to the second. See what happens whenever you have more than two or more than two lone pairs to be donated. Bidentate ligand go on. Okay, these molecules become ring structure. Suppose if I donate it from here, what happens? This becomes a ring structure. So these ring structures are called as chelae. These ring structures are called as chelae. So more is the density, more is the chelation, more stable. It's clear. So this, so you can't form a ring. So there is a small thumb rule. The thumb rule is that there has to be five atoms, one, two, three, four, five, in that ring to make it more stable. So if you have something which will be four and a bidentate ligand and a ring compound is formed, probably you that may not be stable. This is one. So thumb rule is that for a chile, five atoms in the ring and beyond and will make it more stable. Is clear? So similarly, we want tridentate, tetradentate, pentadentate, and most important, of course, here is hexadentate. So what is hexadentate? The best example is edit. Edit is ethylene diamine, tetra acetic acid. Okay, so this is a strong chelating agent. There are six atoms which can donate one pair to a single atom. It's clear. A very popular compound used in estimation of calcium and magnesium ions in water. So discuss the use also. Which compound is used for estimation of ADT, ethylene diamine tetraacetate acid, is hexadentate acid. That was a question also asked. Which is a hexadentate acid? Okay. So normally for animals like pet dogs and cats, if they have a metal part, because they go on, what they call eating anything in the house. Sometimes metals can get it, and they can get poisoned. So the first step is they get EDT. EDT can chelate with metal. And this is an example use of coordination. Another example. Suddenly, if your pet, dog or cat gives out some what they call symptoms of a metal pipe, where you will get EDT. You can't get EDT. What is the other alternative? Take egg, remove the yellow part, make a this thing of the emulsion of the white part, and give two three eggs the white pipe. Because that contains sulfide ion. Sulfide ion is a monodentate ligand. So what is going to do? It's going to join with the metal, and what will happen? To become a complex, this toxicity. Simple medical use of concept of coordination just to keep you coordinated with boring time. Right? Of course, you have to know where we can use these things. So I said tetradentate, I am not hexadentate was very important. So this was about ligands. This one. Yeah. So this was about ligands is chart, is density. Okay. And then what we come to is the next part, that is we are talking about nomenclature. Nomenclature of coordination. IUPAC. It is very clear. It is IUPAC nomenclature of coordination compounds. See, basically, when you have a salt, what does that mean? Salt says you have one and okay, I'm taking a very simple there are statements to write. Correct statements, half an hour going. I quickly briefed you. Take 5, 6 examples. Things you can see. What if they say? Whenever you write the name of the coordination complex, cation is written. Cation is written. Cation is written irrespective of the fact simple cation fashion or a complex. take space to take, and I will follow, and I will follow. Now what happens? We know that whether it's a complex cation or complex, we will take the complex only. This is the whole story is for that. Nobody wants to write about. There's no room for simple cation or a simple anion which forms, just to balance the residual balance in charge of the. So first, what you do is you write down the name. Very simple. Ligand is simple. Ligand is simple. If there are same type of ligands, then you put a multiplying di, tri, tetra, and so on. First, second point, third point is if your ligand itself has a multiplying, for example, dimethyl glycol. So you cannot say in that example, you remember I told you D and G twice. You can't say dimethyl glycol. So in that case, so if ligand itself has a multiplying, if ligand itself has multiplying preference, then use bis, tris, tetrakis in brackets, in parentheses, in bracket. Outside that, you write the multiplying bis, write down the name of the this one. Then what happens after that? Then cation is written first, cation. Then after that, the fourth point, what will you have? Separating. Fourth point, what will you do? Write the name of the central method. Central method item. So here what happens for neutral and positive compounds. Just write the name. The problem happens when it is anionic complex. Anionic complex. Then you write the name of the metal and end it with 8. So for example, if you have aluminium will be aluminum. Can you write ironate? See, the name is derived from the Latin name symbol Fe is from the Latin derived name ferrum. So what will happen there? You write the Latin name. The Latin name is so fair iron will become fair. And so this is clear. So some exceptions to them are there. This is clear. For example, you have mercury. So when you have mercury as a central metal atom in a complex which is an anion, you can't write hydragyrate. Then you use mercury. Antimonate, still binate. You can just antimonate. AT energy. That's just to show that this metal is a part of a coordination stream, which is then the last two, and then we take 5 examples. What we do is after this, after writing the name of the cation, after writing the name of the anion, then we write the oxidation state of the second in parentheses in Roman letters. So we write in parentheses means we are writing in brackets. That is the meaning, but get used to some things. It's clear. I mean, we run a software oriented. One of the biggest problems is our developers are fantastic, but sometimes they can't communicate loud. So I'm requesting you all to improve your English and not know this is a soft skill which you have. But we are having a big problem. We can't live by clients, especially in business. So what we do is we write the oxidations in Roman letters. In parenthesis means in bracket. This was in short, a quick revision I had. We still have half an hour. Let us take some examples. So the examples that I take, let me take the first example. I did 4 examples of the negative anion. So we are very sure about what we are talking about. So we have, let us take this lithium aluminium hydride. Okay. Now remember here there is one more advanced solution. Generally, lithium is not considered for cation. Why? Because there is a certain you are giving me one example. The reason originally this was a hydride. If this was a lithium complex with aluminium, which is something else like nitrate, like oxygen or a nitrogen, then what happens? Lithium, because of its high polymerizing power, what is it going to do? It's going to drag the oxygen out in the complex. Because it was hydride, it is stable. But otherwise, lithium does not form a stable complex. And the ligands have oxygen, nitrogen, so on. Yeah. So that's one more concept we can tell. Okay. Now we come back to our questions. That is how to name this. So you split it. Two steps. Step one, split it. So your cation is lithium plus. Because you cannot have more than one. Because redox reaction we have taught you. Alkyl metals always have a charge of plus one. मनमानी नहीं कर सकता. You cannot say this is lithium two. It's clear. So lithium is plus one. Why? Because alkali metal always it has a charge. It's a salt, cation. So we have aluminium hydride. ये माइनस हो गया. ये माइनस है कॉन्फिडेंटली लिया मैंने because the charges are. So now after this, what is the next step? We find out the oxidation state of this. Let us say the oxidation state of aluminium is X. The charge of each ligand, what is the story I told you? The charge on the complex is the sum of the charge of the central metal atom and the ligand. So both of them are minus one. Here. So yeah, each hydride H minus one. So this will be X minus 4 is equal to minus 1. So X is equal to plus. Okay, define. This has got defined. Now we start with the number. What are the stories say? Come what? First, write down the name of the cation. So cation is lithium. Leave a space. Then we now write down the name of the anionic complex. So when it's a complex, write down the name of the ligand. The name of the ligand is hydride, but whenever you have IDE as the suffix, you will substitute that as IDO. So what happens? And how much is the multiplier prefix? 4. So this becomes tetra hydrido. Okay. Hydride will be written as hydrido. So sulfide will become sulfido. And whenever there is an IDE, okay, it will be written as IDU. Right? Introducing some part here. Tetrahydride. Then what was the metal? Aluminum. But this is negatively charged coordination sphere. So aluminum will be written as aluminate. It will be written as aluminate. And then in the bracket, in Roman letters, Roman letters. In Roman letter 3. Okay, this is the nomenclature. Let me take one more. I mean, here I'll leave the notes because it's complex. So we have the next one. So I'll do the next one. So the second one, I'll take again where the coordination sphere is negative. It becomes easy, continuously sum. So what do we have? Na3, okay, CO, NO26. Is clear? Now I have to teach you ambidentity. So I said there was ligands, types of ligand, monodentate, didentate, tridentate, hexadentate. I skipped ambidentity. Okay, so I'm going to teach you. So here, what happens? So Na, let us split. So we have 3 Na, so that means 3 positive charges. So your coordination complex is 1 NO6. So this fellow is going to minus because these charges are balanced. Three positive charges to balance. So then we get the oxidation state. Oxidation state of cobalt is X minus 6 is equal to minus. So X, this is decided. Now what happens is when you talk of NO2, see NO2, what happens is NO2 can donate an electron to this nitrogen and donate to this oxygen. So such ligands which has two different modes of donating electrons are called as ambidentate. Ambidentate. So this is what I was telling you. You have seen an hexanitro N. Okay. So this was 6. Coordination number was 12. I told you. Why? Because here, in this case, it is donate very rare case. Huh? Normally, it donates only one. The very rare case, it donates two. It's clear. That's why the coordination number is 12. But in the normal course of a study, we'll say that only one gets donated at one time. It's clear. So, अभी क्या होगा? 25. What happened? First, write down the name of the chemist. That is sodium. Okay. Then we have one space left. It is hexa. Now NO2 minus is nitrate. That is ambidentate. How will you write it? So ATE जब ending है, मैंने तुमको एक सीखा. IDE आएगा तो IDO. अभी ATE आ गया तो ITO आएगा. So nitrate will become nitrito. Nitrate will become nitrito. So hexanitrito. Ligand लिखते समय it will be nitrito. But because it's an ambidentate ligand, you have to write it as nitrito N. Hexanitrito N. What does this N signify? Does nitrogen becomes a lone hydrogen. Right? So hexanitrito cobalt. Cobalt लिखिए, cobaltate लिखिए. See, this is -3. So this will become cobaltate. And then you move on to find the nomenclature. Okay. Then one more. So whether so let me just change this to just show it to you. Suppose if you take this one, this is 3Na plus, and then you have Na. This does not exist. I'm not sure it exists. I'm just taking the example just to explain. If this was ONO6, it still be minus. So what happens is in this case, first part of the story is correct. You write the sodium. Here the nomenclature. You said this is nitrito N. Here you will say hexanitrito. O लिखेगा. This way of writing clearly shows you that oxygen is the lone pair. Hexanitrito O. And then we have got what cobaltate. This is just an example. I'm not very sure whether this compound exists or not, but this definitely exists. Okay, so this was just to show the difference between nitrito N and nitrito O in case of ambidentate ligand. Then the next one we can take is we have this K3 Al C2O4. Okay, now look, this is a bidentate. So if I split oxalate is from oxalic acid, C double bond O minus, C double bond O minus. Okay. Now let's see this. Why is this complex stable? Because if I take aluminum plus very rare case. I told you one of the point is that it has to be a what you call transition, or it will be a third period. Elements of the third period. They also have Lincoln assumption. Yeah. That is where the electrons are. Okay. So 1, 2, 3, 4, 5. So there's a ring of 5. This will be state. Now, so when we split it, we have 3A plus and you have AL C2O4 with minus 3. Why? Because we balance the charge. Okay, fine. Now we start. X minus, look at this. Each oxalate ion has two positions to donate it. So we get two minus charges. Okay, I like to write it. It's not a big deal. 2 minus. C double bond. So this was one minus charge, another minus. So 3 into 2 will be 6. X minus 6 is equal to minus. So X is equal to plus. Okay, oxidation state fixed. So what do we have? We have potassium. So we have potassium. Then leave us 6. Then this was right. There's no need to write bis because your oxalate does not have a multiplying prefix. Nickel DMG dimethyl glycoside had a multiplying prefix. इसको directly आप लोग bis just की जरूरत नहीं. It's straight right by oxalate. So AT becomes ATO. Oxalate. Oxalic acid का trioxalate. And aluminium will become aluminate. In bracket. So this becomes the nomenclature of. Okay. So this was 3 examples of a coordination complex which had a complex anion. Complex anion. Now I'll come to something I think my student faced this problem last week. So I will now explain. So look at this. So you have this neutral complex. NR CO6. We have CO. So this was a neutral complex. See what happens in neutral complexes, especially metal carbons. Carbonyl group itself is a neutral because it has no charge and it is attached to a metal. Metal will have charge C. I don't know. He called me up and then I said, "Sir, I remember getting -1." He said, "Nickel -1." To understand one, that nickel here is a metal. Carbonyl group is attached to carbon come to charge, nickel come to charge. Charge का सवाल ही नहीं आता. So what will we call this as totality में? Neutral complex. Call it as a neutral complex. So how will you name it? Same rule. We'll write tetracarbon. Name of the ligand. Tetracarbon. Nickel ligand. इधर nickel and लिखने का जरूरत नहीं. और positive complex and neutral complex. The name of the metal is. For negative complex, diamond complexes, ending suffix AT is introduced. I think now you're doing it. So tetracarbon and nickel group. अब इसका ऑक्सीडेशन स्टेट निकल कर क्या था कुछ भी नहीं था तो छोड़ने का नहीं जीरो लिखने का tetracarbon and nickel zero. So you know that this was a metal. Yeah, so this was one example. Then we will take one more example where we have a positive complex. Okay. So we have Ag NH3. Okay. So now what happens? Split. So there are positive cations. A complex itself. Which name will come first? This is plus Cl minus. So now your what do you call your complex is a positive complex. And how do you name a complex? Same rule. You'll first write down the name of the ligand. So this is 2. So we'll write di, multiply di. Now ammonia, so remember water neutral ligand is called aquo. Amine is called as amine. Okay, so these are names. So this will become, this is not diammonia. Ammonia is given a special name as a ligand. So this becomes diamine. Diamine. Ligand का नाम. Then what do we have? Silver. We have not written argent. Why we have not written argent? Positive complex. Silver. और उसका चार्ज कितना रहेगा? 1. क्योंकि देखो मैंने मेटल क्या एक्सपेक्ट किया, हर बार हम लोग एक फॉर्मूला यूज नहीं करेंगे. X plus 0. Ammonia is a neutral ligand, so कोई चार्ज नहीं है. So X plus 0 is plus 1. So X is plus 1. तो ये हो गया. This is the charge. This is the name of the cation. And then we write the name of the anion, which is chloride. Name of the anion is chloride. Is this point clear? Let's take one or two more examples. We have some time, 10 minutes time, so we will use that very effective. Let's see some. Okay. So here also, you first let me start with this. SCN is thiocyanate. So it can SCN minus generate. It can donate electron to the sulfur. But you also have SCN where it can, so let me write it as NCS minus, where it can donate the lone pair of electron to what we call nitrogen. So what will this be called as? Ambient. So in this case, gain use. How do we name it? So first we will go by our usual rule. What do we have? This is ammonia. So the cation will be ammonium ion, कोई change, complex couple. So X, so when you split it, we got 2NH4 plus अगर ये दो पॉजिटिव चार्ज है, so platinum SCN6 ये हो गया -2. ये हो गया -2. Is this point clear? Okay. Because to balance this +2 charge, we have -2. Then ये तो लिख देंगे अमोनियम. इसका करते हैं X -6. Each thiocyanate has one negative charge. So X -6 is equal to -2. So X will be equal to. So platinum का oxidation state +2. So let us start. Now what do we have? We have this. First write down the name of the cation, ammonium. Then write down the name of the anion. For that you first write. So this will be hexathiocyanate. So thiocyanate became thiocyanate. AT becomes, so thiocyanate becomes thiocyanate. AT becomes AIT or AT. It is thiocyanate. And then what was the metal? Platinum. But ये negatively charged है. हम लोग क्या करेंगे? Platinate. And then inside the platinum, there is oxidation. This is how we do. Then we look at what. Oh yeah, we look at CO7. This where you use this restrictor. CO7 So this is very interesting. We have CO, CN, EN. This is a cation. So last name oxidation state उसका anion ion. But look at this. What do we have? First write the name of ligand. This is a heteroleptic compound. Upaleptic है. Upaleptic मतलब क्या? All the ligands are same. If there are two or more different ligands, heteroleptic complex. Heteroleptic complex. So when there is a heteroleptic complex, what do we do? Write down in the name of alphabet. Okay. तो ये क्लोरो आएगा A B C D, इथिलीन डायमाइन बाद में आएगा. But इसमें क्या होता है? We have like ethylene diamine, डाई आ गया, multiply. तो बाहर से तुम बिस लिखोगे, that will be considered as for the alphabetical order. पहला मैंने क्या बोला? A B C D normal function alphabetical order. But जब बिस ट्रिस टेट्राकेस ये यूज करता है, that is also used to consider alphabetical order. तो फिर अभी इधर गड़बड़ हो जाएगा. You have dichloro and this chloro and this is bis, ethylene diamine, bis by that. We have bis with ब्रैकेट में अंदर लिखना, दो था ethylene diamine. We have ethylene diamine. Okay. Then dichloro goes to chlorons. Then we have chloride. Okay. अभी इसका x minus 2 is equal to plus 1. So x will be equal to 3. So cobalt 3 आएगा. And then we put the word ion because we don't know what is the anion. This is how we do. So ये one more example where we use this. Now that we start points and when you use, right, when you use base trace tetracates, their names are also used while considering the alphabetical order. Di-tri-tetra में alphabetical order consider नहीं करते. Is this point clear? I hope you have enjoyed this lecture. Okay. As I told you, see, we also have a channel called as Plus, where we are discussing what we call as decluttering tips. So what I am doing is while I am teaching, I am coming across and I am revising and looking at multiple choice questions and finding some very unique multiple choice questions. Maybe we will miss in our day-to-day life. And I am slowly enhancing the scope of that so that we will have about 400, 500 questions in that channel, which you can revise chapter wise. So I'm putting 10 questions at the moment, covering up the 30 chapters. Then we'll go on and let's go back. This is a lifelong exercise. So that before your exam, you have 400 critical questions, which will be a sort of revision. Everybody gives lectures, but I have decided to take a different path where I am what you call. So you can go to my YouTube channel, Plus, okay, where we are putting up, and you can subscribe that. You can also buy our product edumate Plus. I am the founder of AKP Learning Solutions Private Limited. We have a product called edumate Plus, where it's a computer-based testing and empowering the student. So we will give the app link. You can, as your teacher completes the portion, you can do test. You can simply first do the first test, which is just a revision of all questions. Then you can go for combined test, and then you can go for mock test. It's there. And this has physics, chemistry, maths for JEE and MHTC students, and just physics, chemistry, biology for NEET students. It's there. So it will help you to empower and gradually at your own pace, what you call, we have 1 lakh questions which are prepared. So you need not buy any other of any subject. That app is quite sufficient. So I'm writing down the name of the app. It is edumate Plus. So I request you to buy this app, okay, from the online. You can go to the channel and buy it. And we meet next week, okay, again at same time next Saturday, same time, 1 more hour. I talk about stereoisomerism and geometrical isomerism and all that I talk. Yeah. And that will be one. And then we will do the more difficult part, that is balance bond and crystal field. So a lot of questions are asked. So I think in 3 lectures, you can condense it. Only I will take 10 course of time. But we condense it in 3 hours. We go to revision. I thank you for joining me today. I hope you enjoyed the lecture. God bless you all. Thank you. And we meet again next week. Bring in your friends, more of them. Everybody should benefit. This is clear. This is a free service. Thank you very much. Have a nice day.